This is Paul Amell, Physics 350, Homework 5, number 2. We have an infinite wire above the xy plane at distance d, and it has a charge distribution of lambda. So we want to know the potential above the xy plane, and we have a grounded conducting plate here, a grounded conducting plate. So the potential in the xy plane is 0. So everything above the plane, we're going to use the infinite wire to find this. And we're going to use the method of images. So we place our image wire a distance equal to the other distance above, that is above the xy plane. We place a negative lambda line charge below. So we end up with something like this, where the potential in the center is equal to 0, as it is supposed to be. We know an infinite line charge has an electric field of this equation right here. We can then find the potential by taking the integral, and our limits are d, the distance from the plane, to a distance s, which is an arbitrary point above the xy plane. And we end up with this equation here. And then we have a potential due to the positive charge, or positive line, which is here, where I noted with an S plus. And then we have a negative line, which is noted here by an S minus. To find the S plus and S minus distance, we draw out our little triangle here, and just with some simple geometry we find this, and then using superposition we add the two together to get our total potential, and we do some math and end up with this. Next we need to find the charge density sigma induced on the plane. From Griffiths equation 2.49, sigma is negative epsilon naught partial normal, where our normal is in the z direction, so it's the derivative of the potential with respect to z, as I wrote here. Then we do some math, and when our z is 0, so we do some more math, and we end up with sigma is the negative lambda times the distance from the xy plane over pi times y squared plus d squared.